Hey folks, welcome back. Today we're going to build on what we've been talking about in the last couple of lectures. In the last few, we thought about series where all the terms were positive, right? We had an infinite series and we were adding the terms a sub 1, a sub 2, a sub 3. And our assumption last time was that all of those a sub n's are positive numbers. Well, that's not true in general. There's no reason why every sequence should always have all positive terms. And so when we build a sum, we're not necessarily adding all positive numbers. So let's look at some examples we've already seen like this. So here we have a series, and if you look at it, you might recognize it's geometric. I'm going to pull out that 4 so we can check that it's geometric. If I pull out the 4, I'm left with 1, and then 2/3, and then 4/9, and then doubling gives us, what is it, 8? 8 fours are 32, yeah. 8/27, and then the next one is 16/81, and then so on. This is what's called an alternating series. And it's alternating literally because the sign changes, right? The sign changes from negative to positive, positive to negative, negative to positive, positive to negative. So it's an alternating series in the sense that the sign changes from positive to negative, negative to positive. But obviously, not every series that doesn't have positive terms has to alternate. You could have the first one positive and then everything negative after that. So alternating series are an interesting example all in themselves. But if we look at this first term is 2/3. The next number here is 2/3 squared. This is 2/3 cubed. This is 2/3 to the power of 4. So this is in fact a geometric series, which I could write like this if I ignore the fact that the signs are changing. Just the raw geometric series that was 1 plus 2/3 plus 4/9 plus 8/27 would look like this. I've got the 4 out the front, and there are the powers of 2/3, and the first power is the 0th power, so we get 1. The next power gives us 2/3, and so on. But we've got this alternating sign, so I'm going to put a -1 out the front and raise it to the power. I'm going to raise it to the power of n. And then just check and see if that works. If I raise it to the power of n, when n is equal to 0, you get -1 to the power of n, which is positive. And then you get -1 to the power of 1, which is negative. And then you get -1 to the power of 2 here. And so I could write this out. And if you check that, it lines up with what we've got here, right? I've combined them. I could write this as -2/3 all to the power of n. But the first one just yields 1. This gives -2/3, so we get the right sign. This is positive 4/9, so we get this value, and so on. So this is a geometric series. We know what it converges to. If it converges, we can calculate that. But it's also a series that doesn't have positive signs for every term. So in this case, the value of r here is -2/3. Right? If I write this out just thinking about it as the geometric series the way we set it up before, this is -2/3 to the power of n, and n goes from 0 to infinity. Okay, so this is our r to the power of n, and this is our c. And we know that if that converges, it's going to converge to a certain formula that we've got. And in this case, the absolute value of r is 2/3, because r is -2/3. We take the absolute value. It's less than 1. And so this geometric series converges. And if you remember the formula, it converges to c over 1 minus r. And in this case, r is -2/3. So this is 4 over 5/3, which is what? 12/5. So this series will converge to 12/5, and it's not all positive terms. And so we can conclude that, we see immediately that series that don't have all positive terms can converge. So let's look at another example that looks at these. This is another example of an alternating series. So if I write this out when n is equal to 1, in fact, I'm going to make this n minus 1 just for fun. If you think about plugging in n equals 1 here, what we're going to get is -1 to the power of 0 over 1 squared, plus -1 to the power of 1 over 2 squared, right? This is when n equals 1. This is the term when n equals 2. This is n equals 3. And so if you start writing those out a bit more carefully, you can see the form of alternating series that we have. And in fact, this is an alternating series because the third term here will be negative, the fourth term here will be negative, and then the fifth term will look like this. That's actually the sixth term, and there's the seventh term, and so on. So this is an alternating series, and you can see it's closely related to a series that we understand. Right? This is very similar to the series you get by just adding the sums of the squares. And given that these two are closely related, essentially the sums of the squares here, if I remove this term, then, you know, we're just adding all the terms, right? We're just adding 1 plus 1 over 1, 2 squared, plus 1 over 3 squared, plus 1 over 4 squared. So it's like we're making all the terms positive. So we're going to introduce an idea known as absolute convergence. And we say a series converges absolutely if the absolute values of all of the terms converge absolutely. So let's go back to this original one we had up here. The nth term in that original series is minus 1 to the power of n minus 1 divided by n squared. And so what's the absolute value of the nth term in this case? Well, the absolute value just makes things positive, right? Whatever the value is, it makes it positive. N squared is already positive, so all it does is get rid of the sign. So it gets rid of the alternating sign we see here. We had a positive and then a negative, and positive and then negative and then positive and then negative. So the absolute value gets rid of the alternating sign. And so we know that those absolute values, right? We know that the series that you make up by adding the positive pieces of all the terms, we know the sum of the absolute values converges because it's a p-series with p equals 2. And so what we can say about this original series is that that original series converges absolutely, which just means that when, instead of subtracting some of the terms, I just add them all, if that resulting series, the sum of the absolute values, this beast, if that beast converges, then we say the original series is absolutely convergent. Now think about what that means. If I say that a series is absolutely convergent, that means when I add every single term, I get something that converges. And so if instead of adding them all, I'm actually taking some away as well, then it kind of makes sense. Because these terms are getting smaller as we go along, because we know it's going to diverge if this limit is not equal to 0. So if the terms aren't getting smaller, then the thing's going to diverge anyway. So if we know we add them all, they become absolutely convergent. If we know we add them all, it converges. That suggests when some of them are subtracted, that's probably going to be smaller, and so it must converge as well. And that's what the first theorem in the book says. It says if the absolute value of a series converges, then the series itself converges. So in a sense, that takes us from the series that we think about that have positive and negative signs all mixed up together in the terms. We can go back to thinking about just the positive ones. And if just the positive ones, when we add them all together, converges, then when some of them are subtracted, the series must converge as well. So what we're saying here is because we know that this series is absolutely convergent, which means when we just add up all of the 1 over n squared terms, we get a convergent series because it's a p-series, p is bigger than 1. So it follows from this theorem that the actual series we started with, the alternating series we started with, itself converges. So absolutely convergent is a stronger thing because as soon as I know that something is absolutely convergent, I know that it converges. So in this case, we were able to say that this series converges because it's absolutely convergent. But not every series converges. Not every series of positive terms converges. And so what happens when we have a series that we know is not absolutely convergent? Because the sum of the positive terms in this series is just, well, the absolute value of this quantity is just 1 over n. And so that's the harmonic series. So the absolute values, when you add them together in this case, give you the harmonic series. We know the harmonic series diverges. If you want to think about it another way, it's a p-test with p equals 1, and that doesn't converge. So what happens with this series, this alternating series, whose absolute values give you the harmonic series? Does this one converge? Because our theorem says that if the absolute values converge, then the actual series converges. But in this case, the absolute values series doesn't converge. And so when we don't have a way to address this question. And so we're going to turn to what's known as the alternating series test. And here it is. It says if you've got a series, and let's go back and think about that previous example I wrote down. We've got a series in that case. We've got a series here which matches up with the idea in this middle box. Let's just concentrate on this middle box right now. We're thinking about an alternating series, and that alternating series has this form. In other words, the alternating part is taken care of with a minus 1 to the power of n minus 1 term out the front. And then everything else is what we're going to call b to the b sub n. So in this case, b sub n is just 1 over n, right? It's what's left. It's what's left after we've taken out the alternating part. So we're going to assume that those are always greater than 0. The way they're defining this, the b sub n are always positive. And so the alternating series test says if you think about that sequence, and the sequence here is just that sequence of numbers 1, a half, a third, a quarter, we're getting our infinite series, our alternating infinite series by successively adding and subtracting those terms. Right? So here's b1 minus b2 plus b3 minus b4 and so on. And in this case, there's our b's. And what the alternating series test does is it says if that's a strictly decreasing series, so in other words, if each b sub n is smaller than the one that came before, which is true here, right? Because you've got 1, then a half, and then a third, and then a quarter. So each one is smaller than the one that came before, but they're all positive. That's what this says. So every single one of them is greater than 0, but b1's bigger than b2, which is in turn bigger than b3, which is in turn bigger than b4, and so on. So you've got decreasing terms, and the limit of those terms goes to 0, then this series converges. And we can see we've got it in this case. I'm not going to worry too much about this stuff at the bottom. Okay, it just tells you how things are behaving. But if we're looking at this example, let's use the alternating series test. We need to show two things in this case. We need it to be a positive sequence of terms, and it has to be decreasing, and it has to converge to 0. So we need to show those things. So let's have a go at using this test to do so. So here's our test again, and I've just written out our series that we're interested in. It's exactly the same series. I explicitly wrote this time the minus 1 to the power of n minus 1. I wrote it out separately out the front, just like it is here. And so we can see, hopefully you can see, that the b sub n is equal to 1 over n, and that's certainly greater than 0 for all n bigger than or equal to 1, and that's what we care about, right? And also, we can think of b sub n being given by a function of n, which is 1 over n, right? So let's think about the function f of x, because if I want to show that b sub n is decreasing, then the neatest way to do it is always to look at the derivative. So let's define the corresponding function f of x. And remember why that's important. Because the b sub n's are coming from that function, right? When I plug in n equals 1, I get 1 over n, which is 1. So that's 1. And then when I plug in 2, I get a half here. And when I plug in 3, I get a third. And 4, I get a quarter. And 5, and I get... So these are the b sub 1, the b sub 2, the b sub 3. Every one of those terms in the sequence that we're adding together to get this series, every one of those terms lies on the curve given by the function y equals f of x, right? Given by that graph. So if I can show that the function's decreasing, then the values must be decreasing in the sequence. That's the idea here. And the derivative here is very straightforward. It's minus 1 over x squared. X squared is always positive, and so that's positive for all values of x bigger than 0, but we only care about greater than or equal to 1, right? And so what this tells us is that b sub n is a decreasing sequence. And that's the key. B sub n is a decreasing sequence. It's positive, and the last thing we have to look at is that limit. What's the limit as n goes to infinity of b sub n? Because that's the last condition of our test. So the limit as n goes to infinity at this time is the limit of 1 over n. And that's 0. That's, hopefully you can see that's 0. That's just a straightforward Calc 1 kind of problem. And so we have satisfied all the conditions. We've got a positive sequence that's decreasing, that converges, and that tells us that by the alternating series test, and I'm just going to use AST here because it's a mouthful to write all of that, but this is the alternating series test. So by the alternating series test, this alternating series converges. And it converges because we were able to show that b sub n is a decreasing sequence. The limit of that sequence is 0 as n tends to infinity, and that b sub n is greater than 0. And you need to show all of those things to be able to apply the alternating series test. Let's have another look at why this might be important. Because this series is interesting. I'm going to go to the next page and we're going to talk about this series a little more. So what we found here is that this alternating sequence, it converges, right? It converges by the alternating series test, but it's not absolutely convergent because the absolute values of these terms added together will give you the harmonic series, and the harmonic series diverges. So we have a special name for a series that behaves like this. A series which converges but is not absolutely convergent is called conditionally convergent. So if the series itself converges, that's what we have in this case, the series itself converges, but when you add up all of the absolute values of the terms, that result diverges, then we say that the series is conditionally convergent. So this series fulfills those criteria, right? The series itself converges, it's not absolutely convergent, and so we call it conditionally convergent. It's just a word, but the series that behave this way can be very weird, so we'll come back to that later. All right, so let's do another one with the alternating series test here. We're going to ask whether this converges, which means we're going to use the alternating series test, right? We want to know whether this alternating series converges, and it definitely is. Think about the first term. You plug in n equals 1, you get, 3 over 4. We get a bunch of terms that look like this. And so it's alternating because of this minus 1 to the power of n minus 1. Notice that I'm always using an n minus 1 there for the reason we start with n equals 1. And if I want the first term to be a positive, which often we do, then that's why we take n minus 1. So the first power of the minus 1 here is a 0th power, which just leaves a positive. But then it's negative, positive after that. Here are the terms. Does this alternating series converge? Well, if we use the alternating series test, we've got two things to check. We want to make sure it's decreasing, and then we want to check the limit. So to make sure it's decreasing, we're going to think about this nth term. In this case, it's 2n plus 1 over 3n plus 1. And that's clearly going to be positive, right? It starts positive. It's always going to be positive. So for all n greater than or equal to 1, that's definitely positive. And that's going to be equal to f of n for some function f. So the function, the continuous function that we can differentiate, that we're interested in to find out whether this is a decreasing bunch of numbers, we look at what the continuous function is doing and ask, is that a decreasing function? So we take the derivative. The derivative of the top is 2, and we're going to multiply that by 3x plus 1. I'm just using the quotient rule. And then the derivative of the denominator is 3, and we get a 2x plus 1, and we divide it by the denominator squared. And then we're going to take that whole thing and simplify, and we find it's minus 1 over something squared, and so it's always negative for all x. Therefore, f is an decreasing function, and from that we conclude that b sub n is a decreasing positive sequence. We've already shown it was a positive sequence up here, and so it's definitely decreasing, and so the last thing to think about is the limit. And if you think about this in a Calc 1 kind of way, you could divide top and bottom by the n's, and what we're left with is 2 plus 1 over n divided by 3 plus 1 over n. Or you could convert it to x's, because it's going to have the same limit as the continuous function, 2x plus 1 over 3x plus 1, and then you could use L'Hopital's rule. And either way, you're going to find that the limit is 2/3. Right, I can't differentiate with n's there because the n's are discrete values and I can't differentiate discrete things. But if I turn it into a continuous function which has the same limit, in other words, slide down that curve rather than look at the individual dots on the curve, then the limit's going to be the same. And either way, that limit is going to turn out to be 2/3. And that's not 0. And because that's not 0, this sequence cannot converge according to the alternating series test, right? We think about this with the alternating series test. We've got to show it's positive. It is. It's decreasing. It is. But it doesn't have a limit being 0. And so the alternating series test doesn't apply. And so what can we do with this series? Well, remember way back in the previous section, in section 11.2, when we first introduced series, we talked about the divergence test. This suggests there's a problem, because the divergence test says that a series will diverge if the limit of the terms is not 0. And so just going back to our original series here, a sub n is that full the full terms in the series we're interested in. And so following up on the limit we found when we were just looking at the positive parts of them, the limit of a sub n, just looking at this thing, we know we already found what the limit of this is as n goes to infinity. It's 2/3. But as n goes to infinity, this keeps flip-flopping. This keeps going positive, negative, positive, negative, positive, negative. And so if you looked at the limit, eventually what's going to be happening is we're going to be bouncing between two numbers that are almost 2/3. but one's going to be positive, the next one's going to be negative, and the next one's going to be positive, and the next one's going to be negative. Some other stuff might happen at the beginning. I don't know what happens back then. But eventually these numbers are going to get really close to 2/3, but they're going to keep flipping between positive and negative. And so that means that the limit does not exist. And our divergence test says that if the limit's not 0, then the series diverges. Well, the limit is certainly not 0 here, right? The limit doesn't exist. It flips between 2/3 and minus 2/3. The limit's not 0, and that tells us that this summation that we started with, this full thing up here, does not converge. So in fact, not only does it not converge, that means it diverges. So we can see that this diverges, and I'm deliberately pulling back some information here about the earlier tests we talked about, because they're important to bear in mind. The fact that the limit of the terms is not 0 means that the series can't converge. So alternating series, not alternating series, this test doesn't say anything about that. It just says if the limit of the terms does not go to 0, then the series diverges. And in fact, we could have said that right from the beginning, right? We could have gone back here and said, does this converge? And just looking at it, we looked at that and we said that limit's 2/3. Call on the divergence test immediately. Tell me it doesn't converge, it must diverge from the divergence test right when you look at it. So it's something you should think about when you look at a series. Before you do any of this hard work, is it going to diverge by the divergence test? Because if it does, you're done. All right, so let's leave it there today. We're going to do more of these examples tomorrow and think some more about this alternating series test, because it's an important test for these series that don't have all positive terms. I hope you're doing well, and I'll see you again soon. Bye.